Hello.
Yes, yes,
Yeah, so we can start now, right?
yes. You can start.
Yeah, okay. So the first problem, uh, let's start. That which of the following is diagonalizable over R? Okay, there are four matrices given, so we have to tell that which of the following are diagonalizable over R. So you can try for 1 minute and uh, write your answers. I can see you on the chat box. Only A. Someone typed A. Okay, so which of the following is diagonalizable over R? So you must keep in mind that the diagonalizability is asked over R. So the eigenvalue matrices must lie inside R. Okay, first thing is to be checked. So option A, we will solve option by option. So what is the option A? That given matrix is, let me call it A. Okay, so what are the eigenvalues? Characteristic polynomial of this matrix is CAX. All the eigenvalues are 1 because the diagonal element, it is a upper triangular matrix and the diagonal elements are 1. Okay, so all the eigenvalues are 1. So the characteristic polynomial will be x minus 1 whole cube. So there are ways to know how when a matrix is diagonalizable. There are 3 or 4 theorems. You must have learned about it in last days. So here, easy way is to see that what is the minimal polynomial of this matrix. Okay, so minimal polynomial of this matrix is not x minus 1. First of all, it will be a factor of this because minimal polynomial divides the characteristic polynomial. So it will be a factor of this. So x minus 1 is not the minimal polynomial. Why? Not the minimal polynomial. Minimal polynomial. Okay. Why it is not the minimal polynomial? Because you can verify it by hand. Just put a in place. I is not equal to 0 because a is not the identity matrix. Okay. So the minimal polynomial, from here we conclude that minimal polynomial is not the product of distinct linear factors, right? Because the minimal polynomial is either x minus 1 to the power 2 or x minus 1 to the power 3, whatever be. We don't care because we know that the minimal polynomial is not the product of linear factors, so the matrix is not diagonalizable. Okay, because a matrix is diagonalizable over a field F, provided that the eigenvalues are there, if and only if minimal polynomial splits into distinct linear factors. Okay, so the first one is not. What about the second one? This matrix. So how do you know about this? So is this? So see, let me tell you that how quickly you can uh, determine that it's diagonalizable or not. So A is this matrix, right? 1 1 1 0 1 0 0 1 0 1. Okay. So what are its eigenvalues? eigenvalues is 2. And what are other two eigenvalues? Why eigenvalues 2? Let me know you. Okay, because the matrix, each row sum is, each column sum. If you will add the columns, 1 plus 1, this is 2, this is 2, this is 2. So one of the eigenvalue must have 2 as an eigenvalue. This you know, I think, right? Okay. So 2 is an eigenvalue and the matrix columns are linearly dependent. So the rank of matrix is not 3. It means the determinant is 0. If the determinant is 0, if the determinant of A is 0, then 0 must be an eigenvalue. So one eigenvalue is 0. Now, one another eigenvalue would be the 2 plus 0 plus lambda, say that is lambda, right? Must be equal to the trace of matrix. The trace of matrix is 3. So from here we conclude that lambda is 1. The eigenvalues of the matrix are 2, 0, 1, all belongs to R and are distinct. Okay. So the minimal polynomial is x minus 2, x minus 1. Again, the product of distinct linear factors. So this matrix will be diagonalizable. Okay. Is it clear to everyone, right? So what about the next option? So this one, see. Here you can see that 4 is an eigenvalue. Why 4 is an eigenvalue? Because lambda is an eigenvalue. Lambda is an eigenvalue of a matrix M n cross n f if determinant of a minus lambda is 0, right? So here if you subtract 4 from the diagonals, so the last row becomes 0, right? Yeah, someone unmuted. So the last row becomes 0. It means 4 is an eigenvalue, right? 4 is an eigenvalue. Okay, see. 0 minus 1, 1, 0, 0, 0, 2, 1, 4. Okay, so you can also break this into block matrices of 2 cross 2, and this is a block diagonal matrix. So the eigenvalues of this matrix would be eigenvalues of this matrix and this matrix. Okay, if you don't know about block diagonal matrix, don't worry. Okay, I will let you know how to calculate eigenvalues in easy way without knowing about the block matrix at this moment. Okay, so 4 is an eigenvalue, is clear to everyone. 4 is an eigenvalue, right? And the C, if something is eigenvalue of this matrix, say I, right? Because the eigenvalues of this matrix are I and minus I. So you can calculate that. That's easy, right? So if you subtract I from the diagonals, right? This matrix would be, so these two will be, these two rows as a rows of 2 cross 2 matrix will be linearly dependent, right? Because we have zeros on the last row. So still as a row of 3 cross 3 matrix, they will be linearly dependent. If you don't know about the block matrix, okay? So the eigenvalues will be 4, I, and minus I. So the eigenvalues lies outside the field. So the matrix is not diagonalizable over R. And the last one, how do you know about the last one? It's easy. Okay. See that this matrix has eigenvalue 0, 0, and 0. Why? Because this is a nilpotent matrix, right? See, if you will square it or cube it, it will become 0. How do I know about that? First of all, 0 is an eigenvalue because the determinant of this matrix is 0, right? 0 is an eigenvalue. And the 0 is 2 times eigenvalue. Why? Because the rank of matrix is 1. Okay. So geometric multiplicity of eigenvalue 0 will be rank of A. Hmm? Rank of A. Rank of A is 1. It means the algebraic multiplicity of 0 is greater than equal to 0. Wait. So 1, right? So let me tell you in another way, okay? That why the eigenvalues are 0, 0. So zero is an eigenvalue, that's clear, right? Zero is an eigenvalue of, I will say it A. Okay, A. So geometric multiplicity of eigenvalue 0 is n minus rank A. Okay, n is the order of matrix. So this is 2. Okay, so I miscalculated that. So it means the algebraic multiplicity must be greater than equal to 2. Okay, so 2 times at least 0 is the eigenvalue. But the another 0 plus lambda, the third eigenvalue, counted with multiplicity, if it is 0, must be the trace of matrix, that is 0. So again, it's 0. The eigenvalues are 0, 0, 0. And so it is a nilpotent matrix. Because the eigenvalues of a matrix are 0, then it's a nilpotent. And a nilpotent matrix is diagonalizable only if it is non-zero. You had done this, right? That a nilpotent operator is diagonalizable only if it is 0. Okay, so that's a not therefore it is not diagonalizable. Okay, so let's move to the next question. Yeah, you can try it for 1 minute. Yeah.
Excuse me, sir.
Yeah.
Sir, for the
Yes.
option B, you told that 4 is an eigenvalue. And yes, we know that 4 is an eigenvalue. The reason you have given, please repeat again.
Yeah. Okay. Reason I have given. Okay. Yeah. The 4 is an eigenvalue because lambda is an eigenvalue of A if the determinant of this matrix vanishes, right? Right.
Yes, yes, sir.
So A minus lambda is nothing but just you subtract lambda from the diagonals. Suppose if you subtract 4 from the diagonals, the last column of the matrix becomes 0, 0, 0. Whatever the other diagonal element, the last column is 0, 0. That's why that determinant A minus 4i is 0. Because A minus 4i, the last column of A minus 4i matrix is 0. So the determinant is 0, right? So 4 is an eigenvalue,
Yes, sir.
right?
Thank you, sir.
Yeah. And for yin minus ir eigenvalue, did you get that?
Yes, sir.
Okay. So let's move to the next question. So suppose G is a finite group. This is a mixture of group and linear algebra. Okay. So suppose G is a finite group and phi G to GL to C is a group homomorphism. Then which of the following is are true? Okay. Every element in the image of G is diagonalizable and other 3 options. Okay. So let me tell you the solution. Let me see if some of you want to answer it. Okay, so let me tell you the solution. Okay, G is a group homomorphism. Phi is a group homomorphism from, it is given to us, right? Phi is a group homomorphism from G to GL to C. Okay, so phi G, every element in the image. Suppose, let's solve it by option. Okay, first option is A. So what? Suppose some element in the image, that would be a matrix. So let's denote it by A. Some element in the image of G. So G is a finite group. Since G is a finite group, G is a finite group. So G to the power order of G is equal to identity, right? This is EG, property of the group, finite group. So suppose, and also let that if it is in the image, then phi G, phi of H equal to A for some H in G. H in G. Okay. So if G is a finite group, then G to the power order G, let's denote it by K. Okay. G to the power K equal to E for all G in G. Okay. So h to the power k is also equal to identity. Operate phi, then phi h to the power k is equal to phi of e. Phi of e must be the identity of gl to c. Okay, so it would be identity. This implies phi h to the power k is equal to identity. So we get a to the power k is equal to identity. So you have a matrix. Every matrix in the image of G satisfies a to the power k is equal to I, right? So what can you say about that matrix? So x to the power k minus 1 annihilates a, annihilates a. Minimal polynomial of a will divide x to the power k minus 1. Okay, so this polynomial x to the power k minus 1, you know that all its roots are distinct. So this would be the product of distinct linear factors, and any factor of it will again be a product of distinct linear factors, right? So minimal polynomial in the image of any matrix is product of distinct linear factors. That's why every matrix would be there diagonalizable over C. Okay, when it is no field is mentioned, then you will consider it C. Okay, is it okay, right? So every element in the image of G is diagonalizable. The second option says that there exists at least an element in the image G which is not diagonalizable. So this is wrong because first one is true. And the for third and fourth, I will leave an exercise for you that suppose you have okay, so a homework is that suppose you have a set of matrices, okay, finite set, all are commuting, then prove that they would have a common eigenvector over C. Okay, then solve option C and D. Okay, so let me leave it as an exercise. So yeah, any question? Otherwise, I move to the next question. No? Okay. So the next question is, which of the following implications are true for A matrix in MNC? A square is invertible and diagonalizable, then A is diagonalizable. A is diagonalizable, then any polynomial in A is diagonalizable. And the last one, A square is diagonalizable, implies A is diagonalizable. Yeah. I will wait for 1 minute, okay? Because of the time constraint, I can give you less time. But still you can try. Let's call these implications 1, 2, and 3. Okay? 2. Okay, so some replied 1, some replied 1. Okay, so let's see what are correct options. Okay, so A square, first of all, let's see the last one. Okay, A square is diagonalizable, then A is diagonalizable. So how do you think about such examples? If you want to counter it, A square is diagonalizable. First, try to take some non-diagonalizable matrix. First, try to think about some non-diagonalizable matrix. Then the easy example comes to your mind is non-zero nilpotent matrix, right? So let's fix n. Okay, order of take that order of matrix. Could fix the order of matrix 2. Okay, so n equal to 2. So this matrix A is 0, 1, 0, 0. This is non-zero nilpotent. Non-zero but nilpotent. So it is not diagonalizable. So if we square it, then it's going to be 0. right? Everyone can verify it. So A square is zero matrix, diagonal matrix, so diagonalizable. But A is not diagonalizable. Okay, so for the third implication, third implication is not correct. The counter example is take A equal to 0, 1, 0, and A square comes out to be 0, 0, 0, diagonalizable. Diagonalizable, but A is not diagonalizable. Okay, so what about the first one? Now it is given that A square is invertible. So you cannot take nilpotent matrix in place of A, right? Because in that case, A square will also be nilpotent. The eigenvalues will be 0. So it will not be invertible. So A square is now invertible. Invertible and diagonalizable. So what does this imply? If it is invertible, this implies that no eigenvalue is 0. No eigenvalue of A square is 0. And minimal polynomial of A square is product of distinct linear factors, right? Because A square is diagonalizable, so the minimal polynomial would be the product of distinct linear factors. And I said that, yeah, right. So let's say that this is equal to x lambda 1, x lambda 2, dot, 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 x minus lambda k, where lambda i's are in C. So A square minus lambda 1, A square minus lambda 2, because this is the minimal polynomial, so 0, right? Because this is the minimal polynomial. So if you put A square, right, I have to put here I, okay? So this matrix is 0, right? So we can write it like this: lambda 1 root lambda 1 I, A plus root lambda 1 I, and for other eigenvalues also, at the last term is this one, okay, I, right? So from here we see that A satisfies this polynomial, dot, 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 right? So x minus root lambda 1 into x minus root lambda x plus dot, 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 x minus root lambda k, x plus root lambda k annihilates A. Annihilates A. So you can see that all these root lambda 1, root lambda 1, and minus root lambda 1 and root lambda 1 are not equal. These are not equal, right? Because no eigenvalue is 0. So these are not equal. Overall, all the roots of this polynomial are non-equal. It's easy to see, right? Because lambda 1, lambda 2, lambda k are non-equal, uh, are not distinct, and none of them is 0. So that's why these all are distinct. Okay, so because it is an annihilating polynomial for A, so minimal polynomial will divide it, right? Let's name it Px. So Mx will divide Px and H distinct and product of distinct linear factors. So A is diagonalized. A is diagonalized, right? First implication is true, and let's leave as an exercise. Let me leave the second option as an exercise for you. Okay, diagonalizable, then any polynomial A is in A is diagonalizable. That's true and easy to verify. You can just verify it by definition. If A is diagonalizable, then there is a matrix, invertible matrix, so that PAP inverse is some diagonal matrix. Now use it and verify. Okay. So is there any question, comment? Yeah. Okay. So this one, this is asked in CSR net exam. No, not 224. This is 2023 December. Okay. CSR net 2023 December. Okay.
Hello,
Yeah.
I'm audible, sir.
Yeah. You are audible.
Yes, sir. Sir, in previous question, I have some counter. I think
For what?
for option A.
Yeah.
That
What counter
A,
example do you have?
the option says that A square is invertible and diagonalizable. Sir, if we take 0, -1, 1, 0, then its
Uh,
square is -1,
0,
0, 0, 1, -1,
0 minus 1.
1 and 0.
Yeah.
Its square is -1, 0, 0, 1, which is diagonalizable and
Okay.
invertible also.
Right.
But it is not.
Diagonalizable. So you are
But A
considering the field
is,
R.
yes, sir. Okay,
No. So
sorry.
you the
Sorry, sir,
field
sir.
is when I will
Yeah.
not mention. I said that
Yes,
the
sir.
field will be considered
Yes, sir.
as C. Okay. So yeah. Let's. Okay. You can try this problem. Okay. Okay, so let me start the solution because I think I have a lot of problems and the time is less. Okay, so let me uh, start the solution. So what question says that let A be an n cross n real symmetric matrix. Which of the following statements are necessarily true? A is diagonalizable. So you must have studied about it in the last days that a symmetric matrix is orthogonally diagonalizable, right? That is a theorem. So the first one is true. A is symmetric. A is symmetric. So A is orthogonally diagonalizable. Diagonalizable. So the first option is true. The second says that if a to the power k is equal to I for some positive integer k, then a square is equal to 1. Okay, let's see. That a to the power k is equal to I. So x to the power k minus 1, let's say it is px, annihilates a. And one thing, first I would solve the option 4. Why? Because it is needed in the second. Okay. All eigenvalues of A are real. So any Hermitian matrix, for any Hermitian matrix, its eigenvalues are real, and it's not difficult to prove. Okay, you can prove it that all the eigenvalues of a Hermitian matrix are real, and a real symmetric matrix is also Hermitian, so its eigenvalues are real. Okay, the fourth one is true. So now I will use it in the second. Px equal to x to the power k minus 1 annihilates a. So it is a annihilating, Px is an annihilating polynomial for a. So the minimal polynomial will divide this, right? So minimal polynomial, I'm denoting it by mx, will divide x to the power k minus 1. So one property of minimal polynomial is that every root of minimal polynomial is an eigenvalue of the matrix. Okay, and you also have to keep in mind that all eigenvalues of the matrix are real here, right? Because A is a symmetric matrix, so all eigenvalues are real, and every root of mx would be an eigenvalue. Okay, so from here we conclude that mx is either x minus 1 or x square minus 1, right? How do I calculate this? Because suppose that First of all, you should know that the kth root of unity may be 1, -1, and all other roots are non-real. It depends on k that whether minus will be a root or not, but all other roots are non-real. They are not real. So mx is a factor of this. So either mx will be x -1 or x square -1. That depends what k is. Suppose k is 4, right? K is 4. Then mx divides x to the power 4 -1. So x to the power 4 -1 is x square plus 1, x square -1. So from here, you see that mx is maybe mx would be the factor of this, because no non-real root should be root of mx. Okay, it would be factor of the that part which has real roots, right? So in any case, we can say that mx divides x square -1, because either mx is x -1 or x square -1, but it will divide x square -1, right? So mx is equal to qx times x square -1. Now put, no, sorry, mx into qx for some polynomial would be x square -1. So put a, then you get a square minus I equal to ma 2x. Since mx is minimal polynomial, so it is 0. From here, we conclude that a square is equal to I. Okay. Right. So the option 2 is correct. Now the third option, that if a to the power k equal to 0 for some positive integer k, then a square is 0. So for third option, a is diagonalizable. We know diagonalizable. From the first option, we have that a is diagonalizable. And third option say that a is nilpotent. So what can you say about nilpotent? A is nilpotent and diagonalizable. So A must be the zero matrix, because non-zero nilpotent matrices are not diagonalizable. So A is zero matrix. This implies A square is also 0. So the third option is also true. Okay. So we can move to the next question. Is everything clear in this? Okay. What this problem says, suppose A belongs to M and C is a matrix of order n cross n over C, such that each non-zero vector of Cn is an eigenvector of A. Prove that A is equal to lambda, a scalar multiple of identity, right? We have given that every vector is an eigenvector, every non-zero vector is an eigenvector. So we have to prove that A must be the scalar matrix. How do we prove this? Okay, see, suppose my claim is that A has only one eigenvalue. Okay, one eigenvalue that would be named lambda later. So suppose lambda 1 and lambda 2 be two eigenvalues. Okay, two distinct eigenvalues. Let us assume that it has two distinct eigenvalues. So then ax1 equal to lambda 1 x1 and ax2 equal to lambda 2 x2 for some x1 x2 belongs to Cn, but they must not be 0. Okay, say x1 and x2 are eigenvectors. So as it is given that every vector is an eigenvector, so x1 plus x2 must be an eigenvector, right? And let me tell you that x1 and x2 is not going to be 0. Why it is not going to be 0? Because the eigenvectors corresponding to distinct eigenvalues are linearly independent. You already have familiar with that, right? So by given hypothesis x1 plus x2 is an eigenvector corresponding to some lambda, right? So we have ax1 plus x2 equal to lambda x1 plus x2 for some lambda. So what is ax1? Ax1 is lambda 1 x1 and ax2 is lambda 2 x2. So this comes out to be this. Okay, solve this, then you get lambda 2 x2 is equal to 0. As I said that the x1 and x2 correspond to distinct eigenvalues, so they must be linearly independent. So we have a linear combination of 0, so these must be 0. The coefficient must be 0. This implies lambda equal to lambda 1 equal to lambda 2, which is contradiction. Okay. So A does not have two distinct eigenvalues. What does it mean? That all the eigenvalues of A are same. So characteristic polynomial of A is x minus lambda to the power n, right? Okay, can any one of you make it now? Solve further. Can you prove that A is equal to lambda I based on what you have learned about the diagonalizability in last 2 days? You can use some theorem about the diagonalizability which relates to eigenvectors.
Sir,
Yeah.
sir, just I'm giving a rough idea only. Actually, lambda 1 and lambda 2, these are two eigenvalues, and x1 plus
No,
x2.
you don't have to go there. You just now you have this x minus lambda to the power n. You have to prove that A equal to lambda I using this.
No, so I was speaking about the other method.
Okay. So no, we can talk about that later. So
Okay, sir.
yeah, okay. So what we have given? So given is that every non-zero vector is eigenvector. So A has n linearly independent eigenvectors also, right? Linearly independent eigenvectors. You can take E1, E2, En. But E1, E2 means these are the E1 means 1, 0, 0, 0. Ei means 1 at ith place and other places are 0. Okay. So these are the linearly independent vectors. So a matrix with n linearly independent eigenvectors is diagonalizable, right? So A is diagonalizable. A is diagonalizable. So what is minimal polynomial of A? Minimal polynomial of A must be product of distinct linear factors and is a factor of characteristic polynomial. So the only possibility is that this should be x minus lambda, because the factor of this polynomial, which is linear, product of linear factor, is the x minus lambda only. And nothing else. We have no choice other than A, right? So x minus lambda is the only choice. Now put A, because minimal polynomial will annihilate. Huh? So if we put A, then it must be 0. So from here we prove that A is a scalar matrix. Okay. So you have learned about 3 things. in the diagonalizability, that a transformation is diagonalizable if and only if it has n linearly independent eigenvectors, and the other is that if and only if the minimal polynomial splits in distinct linear factors. And one more thing is that for a matrix is diagonalizable if and only if geometric multiplicity of each eigenvalue is equal to algebraic multiplicity. Right? These three results are very important in the diagonalizability of matrices. So using these, you can solve the problems. Okay. So every time you will see that I would be using one of these. Okay. So let's move ahead. Yeah, please let me know if you have any doubts here. Any quick question? Okay. So now solve some good problems. Good problems means which are asked in NBHM exam, TFR exam. Okay. So we will solve a problem of NBHM exam which is asked in 2021. Problem is this. But before solving this problem, I would try to prove some result. Okay. So then we will come to this problem. The result is suppose you have a matrix A over some field. This is a very good problem. Okay. A has distinct eigenvalues. All the eigenvalues of A are distinct. Let's take, all the eigenvalues of A are distinct. I should write that A has n distinct eigenvalues. N distinct eigenvalues, and B is a matrix which commutes with A. Then we have to prove that B must be a polynomial in A. What does it mean? That all matrices which commutes with, if some matrix commutes with A, then it must be a polynomial, right? Only polynomials in A commutes with A. Yeah, let's solve it. Proof. So how do we prove? What we have given, let me first suppose that lambda 1, lambda 2, dot, 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 lambda n are eigenvalues of A, n eigenvalues and distinct eigenvalues. Okay. So you have given that B is a matrix which commute with A. So from here, observe that if you have eigenvector A, right? Suppose you have an eigenvector of A corresponding to eigenvalue lambda. So you have given this, right? If you multiply this by x on both sides, then solve this. Bax is, because Ax is lambda x, so this becomes lambda times Bx. So it proves that Bx is also an eigenvector corresponding to lambda. Okay, what I said, let me write it here. So suppose x is an eigenvector corresponding to eigenvector corresponding to eigenvalue lambda. Then we have Ax must be equal to lambda x, right? And x is non-zero. So what I said, that ABX is equal to, because A and B commute, we can write is it this equal to BX. So from here, because AX is lambda x, so what I have, because lambda, we can take it out, right? So this comes out to be lambda x. Now, if you have x n cross 1 vector, B is a n cross n matrix, so this is again Bx is a n cross 1 vector, right? So see, write this y, okay, lambda y equal to ay. So this is, if here you have to see that if Bx is non-zero, okay, then it is an eigenvector, because Bx might be 0 also, right? So if Bx is non-zero, then it is an eigenvector, okay, corresponding to same eigenvalue lambda. If x is an eigenvector, then if either Bx is 0 or Bx is eigenvector corresponding to eigenvalue lambda. Okay, so this implies Bx is equal to 0, or Bx is an eigenvector corresponds to lambda. Okay, So we have for any eigenvalue lambda, Vx and Vx eigenspace of eigenvalue. What is the eigenspace? Do you know about that? Yeah, you must know. So x is vector from Fn such that Vx equal to lambda x. It can be 0 also, right? X can be 0. This is called eigenspace for the eigenvalue lambda. Right? It is clear that Bx is always inside E lambda for any eigenvalue.
Yeah.
Yeah. Okay, so see that can any one of you tell me that what is dimension of E lambda? Dimension of E lambda. What would be dimension
And
of the
so
eigen? Yeah, please. What?
Because of
and
distinct eigenvalues.
So the dimension would be.
because A is diagonalizable, so E lambda is equal to n has n dimension.
So E lambda should be the no, A is diagonalizable, yeah, right. The dimension of E lambda for any eigenvalue lambda. Suppose you have fixed
Should be 1.
the lambda 1. Let me know the dimension of E lambda 1. You have a fixed eigenvalue. The dimension of E lambda 1 is 1, right? Because it has n
1, sir,
distinct,
because distinct eigenvalues.
distinct eigenvalues, right? That algebraic multiplicity of each eigenvalue is 1. So the geometric multiplicity must be 1 because geometric multiplicity is always less than the algebraic multiplicity and is greater than equal to 0. So the dimension of is 1. Okay. So if dimension of E lambda is 1 and suppose that you have two vectors x and vx both belongs to E lambda. So what can you say about them? They must be linearly dependent because the dimension is 1. So any two vectors are linearly dependent because if they are linearly independent, then they will span a vector space of dimension 2 inside a vector space of dimension 1, right? So x, bx both belongs to E lambda, so must be linearly independent. So must be LD. Okay. So there exists a mu, so they must be scalar multiple of each other. If two vectors are linearly dependent, so they are scalar multiple of each other. So there exists a mu in F in your field F such that Bx is equal to mu x. And this is for any lambda, any eigenvalue. So what I have proved for any eigenvalue, Bx is equal to mu x, right? Okay, so suppose, so what we have that Bx equal to mu ix for each I. Okay, so far it is clear, right? That if you have eigenvalue lambda 1, then you will get a mu 1. If you have eigenvalue lambda 2, then you will get a mu 2, such that B x is x2. Then you will denote the eigenvector corresponding to eigenvalue lambda 2 by x2, right? So I should write I, xi. Okay. So if you have eigenvalue, suppose lambda 2, then eigenvector is x2. What I have proved is that you will get a mu 2 such that bx2 equal to mu 2 x2, right? Now the key idea of this problem comes is that suppose, yeah. So by Lagrange interpolation formula, by Lagrange interpolation formula, we can find a polynomial in field fx which takes value mu I at lambda I. What do I mean? That you have n eigenvalues, n scalars, right? And you also have n scalars mu1, mu2, dot 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 mu1. So you can find a polynomial of degree n plus 1 or n. So that takes eigen that takes a value mu1 at lambda 1, that takes value mu2 at lambda mu2 at lambda 2 dot dot dot, right? Because Lagrange interpolation formula holds in any field. Okay, is true for any field. Is it fine? Now PA x is equal to PA xi. Can you tell me what Px is a polynomial, okay, in a field. So PA is a matrix. Suppose PA is suppose Px is A0 plus A1i plus sorry A0 A1x plus dot 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 an x to the power n. Then PA is this matrix, okay. A1a dot dot dot. You have put A in place of x. This is a matrix, right? So can you tell me that what PA xi would be? Xi is an eigenvector corresponding to eigenvalue lambda I. So this will comes out to be p lambda I xi. Let me quickly show you it. Okay. So what I said that suppose a I a1 a dot 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 a n. So if you will multiply it by xi, then you can solve it. Okay. So if you will solve it using that axi equal to lambda ixi, then you will get that this comes out to be a0 plus a1 lambda dot 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 an lambda to the power n xi. That's not difficult. Okay, you can do that. So for each I, this holds for each I. Okay. So what do you have? That PA x1 equal to, oh, by the way, yeah, this holds for each I, and p lambda I xi. This is going to be mu I because p takes value mu I at lambda I, right? So this is going to be mu I xi, but mu I xi is equal to bxi. Okay, so this is bxi, and this holds for each I, right? So we have this bx1 dot pa x2 bx2 dot dot dot. Okay, so uh, this we have. Now can any one of you solve it further? I mean, can any of you extract the result? Just one step is now. So what we have? Two matrices. Yeah, please.
Sir, since x1 is not equal to 0, non-zero vector, so PA minus B has to be 0, and so B is a polynomial in PA.
Oh, right. But PA minus B, why it has to be 0?
Sir, because xi's are not 0 because they are eigenvectors.
Okay, so but PA minus B may be some matrix with rank less than n, right? Then
Yes.
PA minus B into some non-zero vector may be G. So only this thing is not going to be to PA equal to B. Yeah.
PAX is equal to BX for all x belongs to Fn.
Right.
Important.
Why?
With since xi are basis of Fn.
Right. Very good. Yes. Since x1, x2 dot 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 xn spans Fn. because they are eigenvectors corresponding to distinct eigenvalues. So they must be linearly independent, and any set of n linearly independent eigenvectors will span Fn. Okay, so suppose you have any vector x, then you can write it as a linear combination of these vectors dot 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 cn xn. Then you see that pax is equal to pa c1 x1 dot dot dot, and solve it. Okay, you will get it comes out to be bx. So we have pa minus b x is equal to 0. So this holds for every vector. Okay, this implies pa is equal to b, right? How did I did that? Why pa is equal to b? That pa minus b is equal to 0. So you can use the previous exercise also, that every vector is an eigenvector C of this matrix, right? So pa minus b is 0. Okay, and you can also see that from here two linear transformation agreeing on a basis are always equal. Like you can use multiple things, okay, to deduce that p is equal to b. So b is a polynomial in A, right? So what did we get? B is a polynomial in A. So that's what we want to prove. So if you have any doubts, then please do ask. Otherwise we go to the question which is asked in 2021 in NBHM exam. No questions? Okay. So
Sir, can you talk about the Lagrange polynomial, the resisted polynomial?
so please, I can give you the reference. You can read it about it in the Hoffman and Kunje. He discussed about it. Okay, Lagrange polynomial. It is used to find it is an interpolation formula. You can read about it. Okay, so
Okay, sir.
yeah. See, now please let me know the answers. You can use the previous exercise what we proved. You can use the previous result. Okay, what we proved just. So please let me know the answers. I will give you 2 minutes for it. You can type your answer true or false in chat box. Okay.
All true.
Please chat box. So uh, all are true. All true. All true. All true. Okay. Okay. So many of you say that all are true. Okay, so any one of you can explain, please. Why the first one is okay? Why the yeah? Please explain one by one. Yeah.
Since A is a real symmetric matrix and B is the B must be a polynomial of A.
Right.
So if eigenvalue of A is if eigenvalue of A are reals, then B is also eigenvalue of B are also reals.
Right.
And since every eigenvalue is distinct in A, so we have diagonalizability of A. So eigenvector must be independent. Every eigenvector of A must be independent. So
Right. Very good.
B, so
Very.
and yeah, B is diagonalizable because it's such
Yeah.
A is diagonalizable and B is a
Right.
polynomial of A.
Right. Right. Yes. Correct. So let me explain it also that A be a n cross n symmetric matrix with distinct eigenvalues. That is, A has no repeated eigenvalue. Let B be a real matrix which commutes with A. Then, from previous result, A B equal to A n A to the power. Okay, let me use K. Okay, because n is the order. Dot 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 A 0 I, right? B must be a polynomial in A from the previous ring. Now we can look at the options that the eigenvalues of B are real. First of all, A is symmetric. A is symmetric. So eigenvalues of A are real. Eigenvalues of A are real. B is also symmetric. So eigenvalues of B are real. Right? Why B is symmetric? Because if you transpose, if you see the transpose of B, then it comes out to be transpose of this polynomial. Right? And the transpose of this polynomial is the same polynomial. Right? B is also symmetric. And there are other ways to see that eigenvalues of B are real also. Okay. So B is also symmetric. So eigenvalues of B are real. If A is a symmetric matrix, then any polynomial in A is symmetric. Okay. So that you learn this thing also. Okay. I have used it. Although we can find the eigenvalues of, because if lambda is an eigenvalue of A, then if then the eigenvalues of PA are just P lambda, nothing else. This is also a result. Okay. So the first option is true. What about the second option? The every eigenvector of, yeah, please someone unmuted it by mistake, I think. Okay, so every eigenvector of A is also an eigenvector of B, right? Suppose X is an eigenvector. Let X is an eigenvector of A. Then Ax equal to lambda x for some lambda is in the field. Okay. See. So Bx equal to AK dot 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 A0 I into X. So as I told you in the last explanation, that this will comes out to be AK lambda to the power K dot 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 A0 X. Okay. So B is the X is also eigenvector of B with eigenvalue this, right? So because if lambda is real, then this is real. Okay. So the eigenvalues of B are real. Also, the B has the eigen x. If x is an eigenvector of A, then it is an eigenvector of B. And let me tell you a result that if fx is a polynomial, I think I have mentioned about it already, but see, then the eigenvalues of fa are f lambda, okay? And there are no other eigenvalues. F lambda are as, because what I have proved here, it proves that f lambda is an eigenvalue. But are there else? No. The answer is no. Okay. So the second one is also true. C, B is diagonalizable. First of all, B is symmetric, real matrix, so diagonalizable. Otherwise, another way is to see that if x1, x2, dot, 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 xn are eigenvectors of A, then they are eigenvectors and linearly independent eigenvectors of A, then they are eigenvectors of B also, what we have proved in the option B. So B has a linearly independent eigenvector, so it's diagonalizable. Okay. First of all, B is real symmetric. It's diagonalizable. If you this is one way, and another way to see it that B has a linearly independent eigenvector, so B is diagonalizable. Okay. B is symmetric, so real symmetric, so diagonalizable. Okay. Okay. So the all three are true. Most of you answered correctly. Okay. So any doubt? Any question?
Excuse me,
Yeah.
sir.
Yeah, please.
So, according to the schedule, we need a 5 minutes break. So, can we take a break now for 10 minutes? Or
Yes.
it is up to you that whatever you told
No,
that will be.
no, I don't want to take break. Okay, but if the students and the participant want to take, then they can take. Who is looking at them, right?
Yes, sir.
I said if the participant want, then they can take the break.
Sorry, sir, I can't hear you.
I said that I don't need a break.
Oh, okay, sir.
Yeah, I can't hear you also.
So,
So I can continue, right?
okay, sir. So we can continue the session.
Yeah, because I have.
Can you hear me?
Yeah,
Can
I have.
continue.
Yeah, good problems. I want to finish them in this 1 hour. That's why I don't want to take a break. Yeah. Okay. So this question is asked in TFR 2024. What it says that let n be a positive integer and a be a n cross n matrix over R. Suppose that a cube is equal to identity, then a is diagonalizable in M and R, right? In M and R. So keep that in mind. Okay. It is asking that it is diagonalizable over R. So there, yeah, this is the definition. So what do you think about it? A cube is equal to I. You have given, right? So x cube minus 1 annihilates A. Let's A. Yeah. So yeah, many of you have raised the hand. Please type your answers in the chat box so that I can see. False, right? Yeah, okay, Deepika, I would answer your question, okay? But yeah, I would answer your question. I have read about it. Yeah, yeah, false. Why it is false? Let me tell you. So x would divide x cube minus 1. So the A, eigenvalues of A inside 1 omega square, right? So if you construct a matrix which satisfy A cube equal to I and whose eigenvalues lie outside the field, I mean whose eigenvalues are also lambda and lambda square, then your matrix is not diagonalizable over R. So how do you construct? So let me construct like this, that 3 cross 3 matrix, take a 3 cross 3 matrix, put 1 here, 0, 0, and put a matrix with eigenvalues omega and omega square. So we can make that, right? How to make that? Let me x square create it, x square plus x. So a matrix with determinant 1 and trace 1. And the put two values minus 2, that be 3, 2, 3. So let me tell you the way how to construct it. Okay. So there might be some calculation mistakes. So please verify that the trace is 1, right? The determinant is 1, right? It's right? The trace of this matrix is 1 and the determinant. But I want the trace to be minus 1. Sorry. Yeah, wait. That would not work. So minus 1. Now minus 2 plus 3. Yeah, this would work. Okay. So how do I construct a example? So what do I want? I want a matrix which satisfy a cube equal to I and whose eigenvalues are omega and omega square also. Okay. So I take a 3 cross 3 matrix. I want to make a block diagonal matrix. In this block, I will put here a matrix which satisfy this, whose characteristic polynomial is this. Okay, x square plus x plus 1. And here I will put a matrix whose characteristic polynomial is this. So the characteristic polynomial of this matrix would be the product of characteristic polynomials, right? This is x cube minus 1. So every matrix satisfies its characteristic polynomial. So a cube equal to I also. This means this matrix will satisfy a cube equal to I also. Since its a characteristic polynomial is x cube minus 1. So its eigenvalues lies outside the field. So it would not be diagonalizable over R. So that's how we make create the counter example. Okay. So this is false. Yeah. So Deepika, you have asked that if B is not real, then what, right? B is real here because B is a polynomial in A. Okay. These AIs are from field because A is a matrix over real symmetric matrix. So B is a polynomial, real polynomial in A, as I proved in the last exercise, right? What I have proved that if A is some matrix in a field, then B is a polynomial in A. The coefficient are from the same field. Okay, so B is real here also. Okay, yeah. If it is not real, a non-real symmetric matrix need not be diagonalized. Okay, because B is real here, so it must be diagonalized. So I think it's okay now. It's clear right now, right? So the another question which is also asked in TFR 2024, a very good question. What says that? It says that if M is a matrix over Q of order n, is such that the characteristic polynomial of A is irreducible over Q, then A is diagonalizable in M and C. So yeah, if you can answer it, let me see. Yes, Akanksha, you can think about companion matrix. In the last problem, okay? So what about this problem? That if you have a matrix true, okay? Okay, is it true? Really? So yeah, why it is true? Yeah, someone said it is true, right? Yeah, Diksha, why it is true? Can you tell me? Yeah, or any one of you want to explain, then please.
So
Take the
I
previous
am
equals to
thinking.
matrix,
Huh?
then this statement becomes false.
What?
Sir, previously you take the matrix
Huh?
to 2 cross 2 matrix to counter the example,
Uh-huh.
counter the statement. Take the same matrix and the characteristics polynomial become x square plus x plus
Right, right,
1.
right. But the diagonalizability is asked over C here, not over Q. The over C that matrix is diagonalizable, right? Over C
Okay.
that matrix is diagonalizable, but it is asked over C here.
Yes, so for the same example, we can see that omega square belongs to C, so A is diagonalizable over M and C.
Yeah, so that would not work to counter this. Okay, this might be true also. Okay, so how it is true? If you say that this is true, then you must know the region, right? Okay, so let me explain it that why it is true. Okay, so A is MNQ is such that the characteristic polynomial of A is irreducible. Suppose solution. Suppose A is suppose P is characteristic polynomial. Okay, Px be the characteristic polynomial of A, which is irreducible over Q. Okay, so what does it mean to be irreducible over Q? Do you know? Then let me tell you. Okay, so if Vx is irreducible over Q, then it means that it does not have non-trivial factors. Okay, whenever you will factor it, then it would be a factor of unit into some polynomial. Sorry, some unit into a polynomial. You cannot factor it in the product of two non-constant polynomials. Okay,
So x square minus 2 we can take.
x square minus 2. I mean, for what you are taking? Are you going to counter this? I mean, do you think that this is false? Yeah, please. Okay, so this is not false. Okay,
Yeah.
let me tell
Yeah.
you why this is not false. So suppose Px be the characteristic polynomial of A, which is irreducible over Q. So I claim that roots of Px are distinct over C. Distinct. Okay. I mean, the root will be in C, right? They are distinct. My claim is this. Why? So on the contrary, suppose that alpha is a repeated root of Px. Then Px is equal to x minus alpha square times qx for some qx in Cx, right? For some qx in Cx. So alpha is also a root. Yeah, by the way, yeah, I have write it here that I'm going to claim that the alpha is also a root of the derivative. If alpha is repeated root of the polynomial, then it is also root of the derivative. see it. P dash x is equal to 2 times x minus alpha into qx plus x minus alpha square into q dash x. Now put alpha in place of x, then this is 0 and this is also 0. So if alpha is a root of px, then it is also a root of p dash x. Okay, right? So alpha is also a root of p dash x. Okay, so this implies that x minus alpha, so p dash x is equal to x minus alpha into tx for some tx in cx, right? Why I have written here cx? Do you know that alpha is root in over c, right? So the polynomial not be over q. Okay, so it must be inside c. So it might be over q also, but it must be over c. So from here, thus x minus alpha divides both p and p dash x, right? It divides px and p dash x. So it must divide GCD of px and p dash x. What would be the GCD of px and p dash x over c? Px is irreducible over q. So what would be the GCD? Just let me know over q.
X minus alpha.
No. Px, suppose think px as a polynomial over q, and p dash x is also a polynomial over q. So what would be the GCD in qx? Px is irreducible polynomial. Okay. GCD of a irreducible polynomial with any polynomial, either px or 1. Okay. So degree of p dash x is less than degree of px. So the GCD must be 1. Right? You can think like that. Suppose you have a prime. Think in integers. You have a prime 13. So the GCD of 13 with any integer, either 13 or 1 or 13, right? In the same way, the GCD of irreducible polynomial over q is either that polynomial or 1. But if the degree of the polynomial p dash x is less than the degree of px, so the px is not going to divide p dash x. It means the GCD in qx is 1. And if f is an extension of q and GCD of two polynomials over q is 1, then the GCD, their GCD is also in fx is going to be 1. Okay, you can prove it. That's not difficult. Okay, let's suppose you have a two polynomials whose GCD in qx is 1, then GCD of those polynomials will also be 1 in the extension. Okay, so this is 1. So x minus alpha divides 1. This is contradiction. Okay, so here I have a little exercise for you, that if you have a field, say f, and k is an extension, and you have two polynomials fx and gx over fx, their GCD is 1 d, then prove that their GCD in kx is also d. Okay, if you can't prove, then you can see in the book of Algebra by R10, in the R10 book. Okay, it's not difficult at all. Just try it in home. Okay, so what does it mean, contradiction? So why this contradiction appears? Because we have assumed that px has repeated root. So what does it mean? Px has no repeated root. So what if px has no repeated root? So characteristic polynomial is the minimal polynomial, right? So thus minimal polynomial has no repeated roots. Polynomial has no repeated root, right? Because minimal, in this case minimal, because your characteristic polynomial has all root distinct. So the minimal polynomial is going to be characteristic polynomial, because every root of characteristic polynomial is a root of minimal polynomial. You know that. Minimal polynomial has no repeated roots. That's why the matrix must be diagonalizable over C. Okay, and it is if it was asked that it is diagonalizable over Q, then this is not going to be true. Okay, if it was asked over Q, so this is true. Yeah. If you have any questions, then please do ask. The next problem is from NBHM 2024 on invariant subspaces. Okay, so any questions? No question? Okay. So, yeah, what is the next problem? It is from NBHM 2020.
Sir,
Yeah. Huh?
sir, please go to the last slide.
Yeah, please.
Sir, we had to prove that ki A is diagonalizable in MNC. Okay. So
Yeah.
why we are proving that it has repeated, it does not have repeated roots?
Yeah. Okay. Why we are proving that there is a theorem you might have studied about in the first lecture of your workshop, that a matrix is diagonalizable if and only if it has. Okay, let me state it clearly. Okay, suppose A is a matrix in M and F. Okay, suppose A is a matrix in M and F, then A is diagonalizable over F if and only if its minimal polynomial splits into distinct linear factors. Its minimal polynomial is the product of distinct linear factors over F, right? Or you can say that its minimal polynomial has no repeated roots. That is the same
Yes.
thing.
Yes,
Yeah.
got it.
Yeah. Okay. So let's solve this question. Yeah, please do not hesitate to ask your questions. Okay. So what is the these are true and false. Okay, you have to determine that which is true and which is false. But x minus alpha is a common divisor, right? It is a common divisor. So what I have given, that let me write it here, over q it is 1 qx, in qx it is 1, so in cx. So, okay, I have given a general exercise also, right? Let's prove it. This is true for any extension. If you have a field and if you have an extension k of it, right? And suppose f is a field and k is an extension, and if you have any two polynomials over f whose GCD is d, then the GCD of those polynomials in k is also going to be d. Yeah. So anyone? Yeah, please write. Oh, okay. So let me solve it. Okay. So no one typed the answer. So let me explain it in the simplest way, that how do you solve such problems? What do you have? What is given to you, that V is a finite dimensional vector space over field F. then we can consider V equal to Fn, right? We can consider V equal to Fn because n dimensional vectors spaces over F are isomorphic to Fn. Okay, so V is Fn. V is isomorphic to Fn. Be a linear transformation V to V. First option says that F is equal to R. Let me also explain it, that what the option says. The trace of T when restricted to W for all T invariant subspaces, because T, since T is a linear transformation from V to V, and if you have an invariant subspace, what does it mean to be an invariant subspace? It means that the image of TW is inside W. So when T is restricted to W, it also a linear transformation of W. Okay, so the first option says that if the field is R and the trace of the restriction of T to all T invariant subspaces, right? Because when you restrict T to an invariant subspace, it will define a linear transformation from W to W. So the trace is 0. Then T is nilpotent. T is nilpotent as a linear operator from V to V. Okay, and the other option says that suppose the field is C and the same thing is true, then T is nilpotent. Okay, so let us solve first the option B. Okay, option B. So it says that if it is true, then T is nilpotent, right? You will think first about the counter example and you don't get because this is true. Okay, so we think that what happens if T is not nilpotent, right? Suppose that T is not nilpotent and this is true. Okay, let us prove it via contradiction. Okay, suppose this holds, suppose, and T is not nilpotent. T is not nilpotent. If T is not nilpotent, what can you say about it? There is some eigenvalue. Just try to generate a, first try to generate a, invariant subspace. Okay, so what are the invariant subspaces? Do you know? You do know. Those are eigenspaces, right? Generated by eigenvectors. Those spaces, right? So if T is non-nilpotent, there exists a lambda belongs to C, which is eigenvalue of T, and non-zero, right? Because if T is not nilpotent, then there is some eigenvalue which is not zero, because an operator is nilpotent if and only if all of its eigenvalues are zero. So if some operator is not nilpotent, then there must be a non-zero eigenvalue. Okay, so W equal to vector space generated by X, where X is an eigenvector. Okay, X is an eigenvector. Eigenvector of T. Let me write it V. Okay, of T. Okay, W is invariant. Everyone know that invariant. Why? Because T of, so what kind of elements inside W? Some scalar multiple into V, right? So T of W, CV, image of any vector under T, is CTV. But V is an eigenvector, so it comes out to be C lambda V. So this is again a scalar. So this is again a multiple of V scalar. So this must inside this W, because the scalar multiples are in W. So this W is invariant. Okay, and restrict defines a linear transformation, is a linear transformation, right? It is given that T can be restricted to a invariant subspace. So it is a linear transformation. What is trace of T? Can you tell me what is trace of T? Trace of T is lambda. Why? Let me tell you. Sorry, yeah, lambda. Because T is one dimensional, W is one dimensional. One dimensional, the dimension of W is 1, right? Because it is generated by a non-zero vector. And so it has one eigenvalue over C. Because C is algebraically closed, okay? So every operator has an eigenvalue. TV is equal to lambda V. So lambda is only eigenvalue because this V is inside W, okay? V is inside W. So lambda is an eigenvector of this T. V is an eigenvector of this T corresponding to eigenvalue lambda. Okay. Let me write it. T restricted to W. Okay. Yeah. Only eigenvalue, which is non-zero. Okay. Because lambda is non-zero eigenvalue. So trace restricted to this invariant subspace is non-zero. So what do we have? We take T to be non-nilpotent. So we get a non-zero eigenvalue. Then with the help of that, we have generated a T invariant subspace. When T is restricted to that space, then its trace is not going to be zero. So we get a contradiction. This is contrary to this. So it means T must be nilpotent. Okay. So this is true. Is it okay? Is it clear to everyone? We have generated a T invariant subspace where trace is not zero. So it is contradiction to hypothesis. So our assumption is wrong that T is not nilpotent. T must be nilpotent. Okay. Nilpotent. Now come to the A. Because if you do the same thing, suppose, yeah. Any question? Yeah. Yeah, please ask. Okay. So let me explain the option A. So if you try to do the same thing for the option A, right? Someone is unmuted, I think. So if you try to do the same thing for option A, then it is no longer true because the non-zero eigenvalue need not lie inside your field because the field is R. So this might not be the true, right? So you might have a linear transformation for which this is true, but still T is not nilpotent. So how do you construct? So let me first take V equal to R square. Okay. So do you know this, that if a one-dimensional space of R square, yeah, R or Rn is T invariant, then it is generated by eigenvector, some eigenvector. Okay. So first, okay. So let me first write here example, then I will let you know that how do I constructed that example. Okay. So example is a T equal to defined by this metric. Okay. So what do I mean? That it will send Tx to this Ax. Okay. So T R square to R square defined by this linear transformation. So what are T invariant subspaces of? What are T invariant subspaces? T invariant subspaces. The T invariant subspaces are 0 and R square and if and no other. Why no other? Because if someone now if you have a T invariant subspaces which is other than the trivial 0 or whole R square, then it must be one dimensional, right? Because the dimension, if dimension is 0, then this is that, and if the dimension is 2, then it is going to be whole R square. The dimension must be 1. Okay, suppose W is not equal to 0, not equal to R square, T a T invariant subspace. T invariant subspace. Then W must be one dimensional, right? One dimensional. Okay, and TV must lie inside V, right? Because if this is T invariant, then image of V must be inside this. So lie inside this. This implies TV equal to some scalar multiple of V. Okay, so this means V is an eigenvector. Vector lambda is an eigenvalue of T over R, but T has no real eigenvalues. You can verify that. Okay, this matrix has no real eigenvalues. So it means no one-dimensional T, no one-dimensional subspaces are T invariant. So we have only these spaces are T invariant. Okay, so T restricted to R square, trace is trace of T, that is 0. When you restrict T to the 0 subspace, then trace of T, that is again going to be 0, because when you restrict T to 0 subspace, then it is 0 transformation, sending 0 to 0. So the trace is 0. Okay, so this example is not nilpotent. This T is not nilpotent. Still, it satisfies this, that for any T invariant subspace W of V, when T is restricted to W, the trace is 0. But still T is not nilpotent. So this is false. So what I told you, that how do you think about such examples? So first try to take the dimension is as less as possible. Okay, so I have take the dimension is 2. So what I think that I try to create an example such that which has no one dimensional subspaces. So which has no one dimensional subspaces means that a transformation which has no eigenvalues, real eigenvalues. I mean, so which has no eigenvalues in R. Okay, so if it has no eigenvalues, then it does not have one dimensional invariant subspaces. Two invariant subspaces, and I create T in such a way that the trace is 0. So when T is restricted to the whole space, when T its trace is 0, when it is restricted to the 0 space, then its trace is 0. So overall, when is T restricted to all the T invariant subspaces, trace is going to be 0, and the our and T is not nilpotent, because eigenvalues lies outside R means they are non-zero. So T is not nilpotent. So in this way, you can create the. I mean, you can think in this way, okay, right? Because if I write some example, then you can, I have a question in mind that how one thinks about such examples, right? I should also explain that to you. Okay, so the first option is false. So in this way, we have solved this problem. So we have more problems also. Now the problems are from GATE exam. This year we have 3 problems. So three problems. So I have 14 minutes. I want to solve these problems. So I want to finish at least 3 problems. I have only 3. I have more problems also, but some gate problems has to be solved. So I have 4 minutes for each problem at least. So let's move to the next problem. Then I will also give you 10 or 15 minutes for ask. Oh no, I think I can't give you, right? Okay, so let's solve these first. Okay, so let A be a MNC be a normal matrix. Consider the following statements. Please write your answers if you can write that if all the eigenvalues of A are real, then A is Hermitian. If all the eigenvalues of A have absolute value 1, then A is unitary. Okay, so let me see. You can quickly figure it out. Oh, sorry. Okay. So both are true options. Why? Let me explain it to you. Okay, that A is a normal matrix. Consider the following statements. A belongs to MNC and normal. So A is unitarily diagonalizable. Diagonalizable. You have read about it, right? In the first lecture, diagonalizable. A normal operator is first, second lecture in anything. So that a normal operator is unitarily diagonalizable. That is, there exists a U belongs to MNC such that U theta equal to identity and U theta is diagonal matrix. Okay. So what we have given that if all the eigenvalues of A are real, then A is Hermitian. So we have A equal to U theta du, right? So to check that A is Hermitian or not, we need to find that A theta is equal to A or not, right? So A theta will be U theta du theta. So this will be U theta theta, and theta means conjugate transport. Okay, uh, d theta u theta. So this comes out to be u theta, but because D is real matrix, all the eigenvalues of the matrix are given to be real. So D is real. So d theta is equal to D, diagonal and real matrix. So transpose of diagonal matrix is matrix itself, and the conjugate of real matrix is matrix itself. So this is again A. Okay. So A is Hermitian, right? Now, if D equal to lambda 1, lambda 2, lambda n such that modulus of lambda 1 is 1. Okay. It is given to us in the second statement. So we have to see that A is unitary or not. To see A is unitary, what do we need to determine? A and A theta, right? So A into A theta will be A is U theta du and A theta is U theta du theta. Okay. So this comes out to be U theta du U theta d theta u theta. Okay. So this is d theta u. So have I made some mistake? Yeah, this is u theta theta. Okay. So right. So what is d into d theta? So if you have d lambda 1 dot 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 lambda n, if you then you will have d theta equal to lambda 1 bar, lambda 2 bar, dot 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 lambda n bar. If you will product these two, then you will get the matrix comes out to be lambda 1 lambda bar, lambda 2 bar, dot 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 lambda n bar, right? So lambda 1 bar can be written lambda 1 square, lambda 2 square, dot 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 lambda n square. But the lambda 1 square is 1. Similarly, lambda 2 square is 1. Similarly, lambda n square is 1. It means d theta is identity matrix. Okay, so this is equal to identity. So u theta identity u, because u is unitary matrix, so u theta into u equal to I. So you get a into a theta equal to I. This means a is unitary. So in this way, you have solved this question. So both statements are true. So please ask if you have some quick questions. No questions, right? Okay. So now I have two questions. Both are from Jordan canonical form. I think I have time to solve one question. So which one should I solve? You can choose. Okay, the first one is this. This is also from the GATE exam. And the second one is this. Okay, let me solve the first the second one. Okay. So read about it. What does it say? That T and S R4 to R4 be two non-zero, non-identity R linear transformations. Assume that T square equal to T. Which of the following are true? T is necessarily invertible. Okay. So take T equal to some idempotent but not zero node identity. This is an idempotent matrix, right? So non-zero non-identity. And why this is idempotent? Because if you will T square, then this is T again. You can do that because T equal to I 0 0 0 in the block matrices. If you will multiply, then T square is equal to T. So how do I construct? I try to construct in such a way that some eigenvalue is 0 and some eigenvalue is 1 also. So it will be non-invertible and non-zero and non-identity. Okay. So T is necessarily invertible is wrong. T is necessarily diagonalizable. Options D. So T is necessarily diagonalizable. T square equal to T. So x square minus x annihilates T, right? T. So minimal polynomial would divide it. So mx would divide x square minus x. This implies mx is x, x into x minus 1 or x minus 1. No. It must be x into x minus 1. Why? Let me tell you. By given hypothesis. Given hypothesis. Because if it is x, then a equal to 0, which is not so. Sorry, t equal to 0, because t is non-zero, non-identity. If it is x minus 1, then t is equal to identity, which is contrary to hypothesis. So the minimal polynomial must be this. So it is product of distinct linear factors again. So t is diagonalizable. T is diagonalizable. Minimal polynomial is being product of distinct linear factors. Okay. So now what about the second and third option? Second says if s equal to s, that the s is also idempotent, then rank of t and rank of s are equal. Sorry, if s is idempotent and rank t and rank s equal, then t and s are similar, right? T and s are similar if this holds. Okay, let's see. So rank t equal to rank s, t square equal to t, and s square equal to s. Let's see they are similar or not. So I will solve this by their Jordan canonical form. So minimal polynomial of both the operators is x into x minus 1. The region is same. Okay. The region is same. So Okay, we don't know about the characteristic polynomial. Okay, so try to write their Jordan canonical forms. So if you will write their Jordan canonical forms, then the number of one in the Jordan canonical form, first of all, the Jordan canonical form will look like this. Okay, star star 0 star 0 0 0 0 star. Jordan canonical form will like this because T and S both are diagonalizable. So their Jordan canonical form is a diagonal matrix. Okay. So if their rank has to be same, what is the rank of T? It would be the number of ones, because the eigenvalue of a idempotent operator are either 0 or 1. Okay. So in the diagonal, either there will be 1 or 0. Okay. Either 1 or 0. But the 1 will be as many times the rank of the T is equal to the number of ones in the diagonal. Is it clear? Rank of T and the rank of Jordan canonical form is same, right? So the rank of Jordan canonical form is the number of non-zero entries. So as many times 1 will appear, that would be the rank of T. So suppose that rank of S is 3, then the Jordan canonical form would be of S is this, and the same Jordan canonical form of T would be. So they have same Jordan canonical form, and two matrices having same Jordan canonical form are similar, right? Because every matrix is similar to its Jordan canonical form, right? Suppose the rank of S is 3, then its Jordan canonical form must look like this, and the rank of T is also 3, then the Jordan canonical form must look like this. So they have same Jordan canonical form. If the rank is 2, then Jordan canonical form would be this. If the rank is 1, the Jordan canonical form would be this. So in any case, their Jordan canonical form is going to be same. So they are isomorphic. Okay. So in this way, I have solved this one, that this is true. T and S are similar if S has only 0 and 1 eigenvalue. So you can figure it out that it is true or not yourself. Okay, let me leave this as an exercise because of the time constraint. I have to stop here. Okay, so you can solve it at home, and it's easy to find and counter example. Okay, for the third one. Okay, so I will stop here, and if you have any quick question, then please do ask. So yeah, this is the last question. And I would also I would wanted to solve it, but I don't think that I would be able to solve it now because I need time to solve this. This is also a question asked in GATE examination from the Jordan canonical form. Try to solve this at home. Okay, you can take the screenshot. Yeah. Yeah, thank you. So you may ask the question.
Sir, can you provide the PDF?
Yeah, sure. I will provide the PDF. Don't worry. Just after this
Thank you,
session.
sir.
Okay. Any
Thank you,
questions?
sir.
Okay.
If there is any questions,
Okay,
they
sir.
can unmute themselves and ask questions.
Sir, I want to ask how to find a T invariant subspace of a linear transformation. That is, suppose that vector space of dimension n is there
Hmm.
exists a T invariant subspace of dimension k less than equal to n.
So it is not always true that there will be a T invariant subspace of each dimension. So it depends on the field, because if you have a algebraically closed field and the minimal polynomial splits, then you can find. Then for each k, you will have a invariant subspace. Okay, so how to find the T invariant subspaces? For that, you have tools like you can take some eigenvalue. Then uh, there are some spaces which are always T invariant, kernel of the transformation, image of the transformation, and if you have some eigenvalue, then eigenvector, eigenspace generated by the eigenvectors and any eigenvector, and if you have two
Okay. No, sir.
eigenspaces,
I
then
want
their
to check
direct
that
sum.
given.
Yeah.
So I want to check that given any linear transformation of finite dimensional vector space n, is there a k-dimensional vector
No,
k-dimensional T-invariant subspace?
no, no.
How do I how to
That's
check this?
that's not always true that there would exist. So it is true in the case that if your minimal polynomial splits over the field, then it exists. Okay. I mean, for each k less than n equal to n, the in T invariant subspace of dimension k would be exist. That can be proved using the induction. But it is not always true that suppose you have a I mean linear transformation from Q4 to Q4, then you can it need not have always of I mean a T invariant subspace of dimension 2 3. Okay, so it need not have a T invariant subspace of uh, non-trivial T invariant subspace. It need not have. So is it clear that what I said to you? So your question is that does there exist a dimension k dimensional vector subspace which is T invariant, right? The answer to this question is
Now
no.
I
That
want to
the
ask that if there exist or not, how to check it?
how to check it? So that depends. Okay, there is no. I mean, I don't think that there is a journal method. It depends on the field. Okay, there is I don't know a journal method. I don't think that there is such a journal method that if you have given some linear transformation and you want to check that there exists some T invariant subspace or not. Okay, so there might exist, there might not exist. So you have to try the different tools. Yeah.
Hello, sir.
Yes.
I have a question. I have a doubt. You have proved the result that if a matrix capital A has distinct eigenvalues and the matrix A commute with another matrix B, then if AB equal to BA, then B is a polynomial in A. You have proved the result. It seems to me that the proof depends on the fact that the geometric multiplicity of every eigenvalue is 1. Yeah. So if the eigenvalues are distinct, then automatically the geometric multiplicities of each eigenvalue is 1. But my question is, if in spite of taking that the matrix has distinct eigenvalues, if we take the weaker condition that all the geometric multiplicities of all eigenvalues are 1, then is the result true?
No, but in that case, you have to see, right, that you have n linearly independent eigenvectors or not.
No, sir. If I take all the eigenvalues, the geometric multiplicities of all the eigenvalues are 1, then is the result true? Because it seems to me that your proof is mainly based on the point that the
Right,
geometric multiplicity.
but at last we have used that the x1, x2, xn spans fn, right? But in that case, we will have not n linearly independent eigenvectors, so we will have less, right? So you cannot conclude that the PA and B are equal because they will be agree on some less part of a basis.
Okay,
Right?
sir.
Is it clear?
Yes, sir. Yes, sir.
Okay, but let me tell you something interesting about that. That if you have a matrix A and B is a matrix, A is a matrix whose characteristic and minimal polynomial are same, then any matrix which commutes with A is going to be a polynomial in A. You can try it at home to prove. Okay.
Yes, sir. Yes, sir. I think that matrix are called derogatory matrix or something like that.
Yeah. Okay. So try to prove.
Okay, sir. Okay. Thank you, sir. Thank you for your reply.
So